Okay, so time for a new chapter, time for a new section, section 7.1. So far what you know about integrals is that you can basically do two things. If it fits your integration table, you are good to go. If it doesn't fit your integration table, the only thing that you can do with it is what?
Substitution.
To make it fit. That's right, a substitution to make it fit the table. Right now in chapter 7, we're going to learn a whole lot of other integration techniques that you haven't learned before, unless you've had this class before, that you haven't learned before. So, have you ever wondered, there's a substitution, that's kind of like the chain rule, right?
Yeah.
Substitution is like the opposite or inverse of chain rule. Have you ever wondered why there's not a product rule? There's a product rule for derivatives, isn't there?
Yeah.
Is there a product rule for integrals?
Not that I know of.
Not that you... I want to show you something. Do you know what that is?
The product rule.
From product rule. I'm going to prove something for you. And we're just going to start with what the product rule is, and we're going to try to undo it. So notice that we've got a derivative, and the derivative equals derivative of the first times the second plus the first times derivative of the second. That's your basic old product rule. Now, what's the inverse of a derivative?
The integral.
Let's integrate both sides. We can actually do this. You can integrate both sides of an equation. So if we integrate this dx and integrate this dx, then what we end up getting is the integral of the derivative of f of x times g of x dx. And over here we got the integral of f prime of x g of x plus f of x times g prime of x. You guys okay with that so far?
Yeah.
Just take an integral on both sides. Now let's see what happens here. What is going to happen here if I take the integral of a derivative?
It's gonna do itself.
Yeah, calculus tells us that. They are inverses. So if I take the integral of a derivative, dx, okay, that's gone. All I'm going to have is f of x times g of x. Does that make sense to you? Are you sure?
Yeah.
Now, the next thing I'm going to do, I'm just going to separate this. Notice that with integrals, you can separate by addition or subtraction. So, I'm going to do that. I'm going to have the integral of f prime of x, g of x, dx, plus the integral of f of x times g prime of x, dx. So, we had product rule. I just take an integral of both sides. No big deal. Derivative is gone. Integral and derivative, they basically undo each other. They're inverses. I have just the functions themselves, f times g. Here, we know this was product rule. If we break up our integral after doing an integral on both sides, we have one integral. We got two integrals. You guys with me? I'm going to solve for this one. I'm going to put this on one side. Basically, I'm just going to subtract that guy. Does that make sense? Okay, so... if I do, then we've got the integral of f of x times g prime of x dx equals, I'm going to keep this, and if I have subtracted that, I'll have f prime of x times g of x dx. Are you guys okay with the algebra on that one? I'm going slow. That I want to make sure you really do follow it. Do you follow it? There's only one more thing that I'm going to do. What I'm going to do right now, I'm just going to switch these two guys around. So by the commutativity of multiplication, this is not a problem. I'm going to put g of x before f prime of x. You okay with that one? Okay, so integral of f of x times g prime of x dx equals, let's see, f of x, got that, times g of x, no problem, minus integral of g of x times f prime of x dx. Okay, I want to show if you feel okay with that so far. Now, that's just some algebra after doing a little bit of calculus. All we did was do an integration on both sides. What in the world does it all mean? Well, I'm going to show you, because right now it's a little hard to understand. We're going to use some symbols right now to represent some of these functions. So what we're going to do is we're going to call u, we're going to call f of x u, and we're going to call g of x v. Please keep in mind, u and v are going to represent functions in your integral right now. They're going to represent some functions here. So we're letting u represent the function of x, v represent the function g of x, a function of x. You guys okay with that so far?
Yeah.
Now, we got some other things besides just f of x and g of x, don't we? I mean, we could change this to a u right now. Are you with me? We could change this to a u. We could change this to a v. We could change that to a v. You with me?
Mm-hmm.
However, we've got an f prime, and we've got a g prime. So what we're going to do is go, okay, cool. Well, tell you what. Let's just do like a du. Let's do a derivative on both sides. If I do this just like your substitutions do, derivative of u is our du. Derivative of f is f prime of x. Dx. Do you remember doing that?
Yeah.
Just like a substitution. Well, here we'll get dv, and we'll get g prime of x dx. You still okay with it? Now look, every one of these pieces is now part of this little box of knowledge. Let's do a substitution. Instead of f of x, what are we calling it?
du.
No,
I mean,
f of x is just
u.
u. What is this piece? G prime of x dv. That's our dv. So this is dv. F of x was u. G prime of x dx, dv. You guys okay with that so far?
Yeah.
Equals. What's our f of x again?
U.
What's our
V.
So f of x is u times g of x is v minus integral. What's our g of x?
V.
Now this is kind of cool. What's our f prime of x dx? This whole piece. So if we integrate the product rule, what we end up getting is this thing right here. What this thing is how to do integration by parts. Just like the product rule is a formula, right? It's a formula. Just like the product rule is a formula, it's been proven. But just like the product rule is a formula, integration by parts is also a formula. And even though it looks a little like, what in the world are we doing? I'm going to give you some easy ways to do some of these integrals. You guys want to see how this stuff works?
Yes.
Firstly, just see how the formula comes about.
Yes.
I don't want to just give you that because like, what in the world? This stems from the product rule. It's an easy proof, but that stems from the product rule. Let me show you why we do this. So integral of x times e to the x dx. So this right here, what's this called again? Maybe write that. This is integration by parts. So when I say do integration by parts, or when the book says do integration by parts, or your best friend says at one of your parties, hey, can you do some integration by parts? You're like, yeah, duh, I know what that means. That'd be the best party ever, by the way. So, my kind of party. So let's look at this for a second. Think through all the things you know about integrals. Does that fit your integration table the way it is? No. This would, that'd be easy. That would, that'd be easy. But this, can you use a substitution?
No.
If you pick this to be u, the derivative is 1. Does it get rid of the x?
No.
That's a problem. So will a substitution work here? No, there's no way to do this integral for us right now. We had to create something new that would take care of it, and this is what we have. You see, when you have a product here, we use the product rule. Sometimes when we have products here, we can use for integrals integration by parts, which is really, really cool. Let me show you how this works, and let me show you what you should be picking for u and for v. By the way, it should be really apparent whether you pick the correct thing or not within about the first step or two. All right. So here's how, in general, you choose how your u and how you choose your v. So a couple little notes. I want you to choose u so that you can take the integral of whatever v is, basically the integral of the rest. It'll make sense in just a second. I'm going to write out the notes right now, write them down, and I'll explain them. So choose u such that, or so that, the integral of v is actually possible. And try to pick u. This doesn't always work, but this is a good indication. Try to pick u so that the derivative of u is better, so that it's smaller or easier to work with. So choose u so that the integral of v firstly is possible, because you're going to have to take the integral of v. Also, and try to pick u, so that the derivative of u is better. I know that's not mathematical, but better as in you reduce the power. It becomes smaller. It goes away completely, something like that. So here we go. I want you to look at this integral with me. There's two parts to this. There's an x part and there's an e to the x part. You with me? Okay, if I pick u to be e to the x, is the derivative of e to the x better?
No.
No, it's still e to the x. I could take the integral of x. That's okay. But if I pick x, what's the derivative of x?
1.
Is that better?
Yes.
Yes, 1 is better than x, isn't it? I think so. I'd rather work with 1 than x. Seems better. Also, can you do the integral of e to the x? Then that's our appropriate pick, our appropriate choice for u. So here's how we do this. It's going to take some getting used to, but here's how it works. Pick u so that you can take the integral of the rest, your v, and pick u so that hopefully the derivative of u is going to be better, easier to work with. Do you follow that? So in our case, we're going to pick u equals x. Here's what v equals. It's really easy to find. There's an easy way to do it. What's your u?
X.
Cover that up with your hand. V is all the rest of it. So v is the integral of e to the x dx. The reason why we have that is because we're going to have to deal with the integral at some point. We have to have our v equals the integral of the rest. We need to be getting, let's see, what are we trying to get there? We want to be able to find our v for this guy. We got to have that. So can you do your, just like you're doing a substitution, can you do your du?
Yeah.
Sure. How much does your du equal?
Yes.
Okay. V was the integral of the rest. Can you do the integral of e to the x?
Yeah.
How much is it?
Yes.
Don't worry about the plus c right now. Don't worry about the plus c right now. We're going to deal with the, say what?
Oh, v.
No, we're just, right here, we're not doing a derivative. We're saying v is the integral of the rest. Okay, we're not doing derivatives here. We're actually doing the integral of this thing. So v is the integral of the rest. That's what v is. So, okay, do the integral of that. V is now e to the x. You with me? Okay, cool. Man, do we have the parts? Do we have what u equals?
No.
Do we have what v equals?
No.
Do we have what v equals?
Yeah.
Same thing. Yes. Do we have what du equals?
Yeah.
Put in the formula. So what our integral is then is u times v minus the integral. Notice there's another integral. You do integration twice here. One to find the v, and then again in your formula. E to the x. I'm sorry, what was the du?
Dx.
That's the idea. I need to make sure this makes sense to you. So we're picking u, so that the derivative becomes easier and you can do the integral of the rest. The easy way to do this, identify what your u is, cover it up with your hand, v equals the integral of the rest. That's what v is for us. That's the easy way to do it. After that, well, find the derivative of u, derivative of x. du equals dx in this case is a really easy one. Do the integral of whatever you had left over. So that's e to the x. Now put it in the formula. Integration by parts says integral of u dv equals u times v minus the integral of v du, dx in this case. Now, can you do that integral? How much is it?
Yes.
So we get x times e to the x minus what? This, when you finish that last integral, that's where you do the plus c. You see, you could get a constant here. You could. But we don't need to because you're saying integral of constant plus a constant, you just get another constant. So we'd have a plus c here. You guys all right with that one? Tell me one more thing that we could do.
Change it again.
We could factor in e to the x. A lot of times with e to the x you can factor it. So what we know is the integral of x e to the x dx actually equals x e to the x minus e to the x plus c, or e to the x times x minus 1 plus c. Either one of those things. Show of hands if you can follow that one. You're probably going to need some more practice, right?
Yeah.
Okay, because right now this is only the first. This is about the easiest that we can do. They get a lot more intense, I should say. Not really any different idea. It's the same idea. If you can't do a substitute, by the way, when you're doing integrals, don't jump immediately to integration by parts. Go through your list. If it fits integration table, that's the easiest, and you just do it. If it doesn't, you try what first?
Substitution.
Please try a substitution, because if you can do a substitution, that'll be easier. After that, then you try stuff like integration by parts. Then you try a trigonometric substitution, which we haven't covered yet. We're going to cover that in this chapter, but that's later on. So, let's try a few more examples. We're going to start building these up to more and more intensity. That way you get used to doing some of these problems. I don't want to give you just like spoon feed you and then on your test just hammer you with some hard ones. So we're going to do some hard ones here in a little while, but I want to get you used to this first. So how about, I'm also going to try to make some mistakes. That way you can see the appropriate choices and when you will realize that you've made the wrong choice. Does that make sense to you?
Yeah.
We go, oh man, that's what happens when you make the wrong choice here. So, okay, we'll take a look at it. Now the first thing we always check for, what is it when we check integrals? What do we check for? We check to see if it's actually in the table first. Is that in your table? Heck no, most of them aren't going to be okay, otherwise it'd be real easy. After it's not in your table, what do you try to do?
Now substitution.
Now you try to do a u sub. Is a u substitution going to work here? If I pick this, the derivative is x squared. Do you see an x squared anywhere?
No.
If I pick this, that's 1 over x. Do you see a 1 over x anywhere?
No.
Then substitution is not going to work. Okay, well if a substitution doesn't work, our next go-to, this is the model of thinking that you do, okay? Does it fit the table? If it does, awesome. If it doesn't, okay, substitution. Does it fit substitution? If yes, cool, that's pretty easy. If not, dang it, then we got integration by parts. It'll still work, it's just a little bit more work. So, go through and try to pick the appropriate thing, the appropriate factor for your integration by parts. So, we got two choices again for our u. Our u could either be x cubed or it could be ln x. What would you pick for your u?
3x to the third.
Why not x cubed? Let's think about it. I want to show you though. Check this out. Let's say that I picked, you can write this down or not, I don't really care. Let's say you picked u equals x cubed. You with me? If you pick u equals x cubed, can you please tell me what your v would be? No, it's not just ln x. Don't forget that integral. My goodness, don't forget that. It's the integral of ln x dx. It's all of the rest of the stuff. Does that make sense? You're basically just covering up the u. The u is one part, This is your u. V equals all of the rest of the stuff. So V equals, quote unquote, the rest. Show of hands if you feel okay with that. It's a big deal. All right. Now, could you take the derivative of this?
Yeah.
And we can take the derivative of darn near anything. And that actually makes it easier for this one. Can you take the integral of ln x? You can? What is it?
The 1 over u. 1 over u du.
Okay, I'm not asking for the derivative. I'm asking for the integral.
1 over
The derivative of ln x is 1 over x. What's the integral of ln x?
e.
No, it's not e.
Oh.
Well, I don't know. What is it? Can you do it?
No.
Can't actually.
Then if you can't do it, then we've picked the wrong thing. Does that make sense?
Yes.
You need to pick, listen, this is not a trivial point here. You need to pick u so that hopefully the u becomes better, the du makes it better. But if not, okay, the main thing here is that you can actually do the integral of v. Because if you can't, then you're stuck. None of you right now, unless you've had this class before, know what that integral is. Do you know what the integral of ln x is? No, you don't. So we made the wrong choice. This is a bad choice. Well, if that's the bad choice, don't beat yourself up over it. Just erase the problem and pick the different thing. What should our u actually be?
ln x.
Okay, cool. What you said all along, genius. So, if u equals ln x, can you please write down what the v is going to equal?
So that'd be 3x squared.
No, it wouldn't be 3x
No,
squared.
Integral of
Yeah.
x cubed dx.
Too much. Too many things.
We still got an integral, don't we? Listen, I'm not lying to you. All you do is cover this up, cover that up, your u, and write the rest. Whatever you see, that's what goes for your v. It even rhymes. Don't you love rules that rhyme? Whatever you see is what goes for your v. Whatever. That's stupid. I should edit that. I'm not going to. You can watch it. Go.
V is for victory.
Yeah. I feel victorious right now. Can you take the derivative of this guy?
Yeah.
Okay, what's the derivative of ln x?
1 over x.
Hey! The only thing where the derivative equals the integral is when you're dealing with e to the x. Okay, that's it. ln x is different. So we get 1 over x. Ah, good. Now, with the v, we're not doing derivative here. We're actually solving this integral. Can you do the integral of x to the third? Then we've picked the correct choice here. Okay, the other choice didn't work. This choice, we'd get x to the fourth over 4, or 1/4 x to the fourth. I don't care how you put that. We don't need a plus c, because we're just using this in our formula right now. We'll have the plus c at the very, very end. Show of hands, feel okay with that one? And do you understand why we picked the u the way we did?
Yeah.
Good, that's important. That's the hardest part of this, is picking the u correctly. Honestly, it is. The rest of it is a formula which you know how to do. You know how to do easy integrals. You know how to do all sorts of derivatives. You're good to go. Just use the formula. So what the formula says is that the integral of u dv equals u times v minus the integral of v du. Just plug in the pieces. Watch this real careful though. Make sure you plug in the pieces correctly. Can you please tell me what the u is? Good, right here. That's our u. Times our v. Do the v that you actually solved for. Don't put the integral again. What's the v?
X to the fourth over 4.
You guys okay on the u times the v? We got a minus sign, put a minus sign. We got an integral sign, put an integral sign. Put the v here again. The v goes in 2 spots. V goes here, v goes here. Now, stick with me. ln x, x to the fourth over 4, minus sign, got it. So ln x, x to the fourth over 4, minus sign, integral, integral, x to the fourth over 4 again, that's our v. Now, look at your du. Your du is not always dx. Your du depends on what you picked for your u. What's your du?
1 over x.
So we need 1 over x dx. It's different than substitution. It's different. You don't start solving for the dx here. The formula says you're going to take this and put this whole thing where this is. You don't start solving for that, like some people do, and like I do for substitutions. So if your u is ln x, put that. If your v is x to the fourth over 4, put that. minus, no problem. Integral, no problem. V is x to the fourth over 4, put that. Du is 1 over x dx. Show of hands if you understand the concept. Good. Now, simplify it, solve it. This should be solvable. If it's not solvable, listen carefully please. If this isn't solvable, it's the only piece of calculus you have left, right? If that's not solvable for you, if you can't do that, try a substitution. Or try another integration by parts. If this thing explodes way bigger than this thing, then you've picked the wrong choice and tried the other substitute, try the other u, okay? So you shouldn't be making these way, way worse. They should start getting better, smaller powers and things like that, okay? Or a doable integral. This will actually get the same power back, but we can do the integral. So in our case, we got ln x times x to the fourth over 4 minus the integral. What are you going to do with all this stuff? Tell me something you can do.
Combine
Combine. How much do we get?
x to the fourth over 4x.
Not x to the fourth. No.
X to the third.
X to the third, yes.
Ah.
And then we can also do what?
Bring the 1/4 out.
Maybe 1/4 out front would be a good idea. Hey, does that look like something you can do?
Yeah.
I sure hope to goodness that you can. I mean, that should be an easy one. You guys okay with the algebra on that one?
Yeah.
1/4 comes out. X to the fourth. You should know how to simplify here.
Yeah.
So let's keep after it. This one I'm going to write a little bit different because I don't like having my ln x first. So I'm going to write 1/4 x to the fourth ln x. Y'all okay that that's the same thing? 1/4 x to the fourth ln x minus 1/4. Hey, look at that. Now we can do an integral of something that's really, really, really easy. What's the integral of x to the third?
1/4.
In fact, we already did it.
Yeah, I think 1/4.
Now is where you put your plus c. Is the plus c important?
Yes.
So don't forget it, okay? So don't do all this work and then go, I'm done. No, you're not done. Put the plus c. Let us know that happens. So 1/4 x to the fourth ln x, no problem, minus 1/16. See where that comes from?
Yeah.
Yes, no, everybody?
Yeah. X to the fourth.
X to the fourth.
Let's see.
Could you do some other things with it?
Factor out x to the fourth.
Yeah.
Oh, x is
You
1/4.
could do
x
a
to the
lot of
fourth.
things with this,
Factor
okay?
out x.
You could factor in x to the fourth. You could actually force this thing to factor out a 1/16 or a 1/4 or a 6. You could factor out a lot of stuff here. So if you did, it's going to look a little different. So keep in mind when you look in the back of your book, if it looks different, they might have just started factoring things. So don't give up on it. If you go, man, I think I'm right, try factoring something. See if you can see a common factor that they have. Okie dokie. Show of hands feel okay with that one. Can we build it up just a little bit? Okie dokie. Okay, I'm going to change this problem slightly in just a moment, but I want to ask you a question first. What do you check first when you're doing
in your table.
integrals? Table, okay, good. Does it fit your table?
No.
Next, you check for,
Substitution.
will a substitution work here?
No.
Look again, will a substitution work here? Absolutely.
Yeah.
Because the derivative of this is
2x.
6x squared. Do you see it? Your x's are gone. So if I give you this problem, this is my whole point, which some of you obviously didn't listen to. My whole point is do not jump automatically to that. That's silly, okay? Try a substitution if it'll work. Here, don't do this problem. I told you I'm going to change it in a minute. So this would be great for a u sub. U equals this, derivative of 6x squared. X squareds are gone. You pull out a 1/6. You're basically done. You're going to get negative cosine. 1/6 negative cosine of 2x cubed, if I'm right. Plus c. Done. Easy. Will a substitution work now? No.
No.
No. So what are we going to do?
Part.
The next one. You always check a substitution before you check integration by parts. I hope that I'm getting through to you right now. I'm getting through to you right now? Always check that because it'll make it easier if it'll work. So, oh man, let's see here. What's a good choice? What do you think? Sine 2x. Well,
2x.
if we pick, say what now? If we pick sine 2x as your u, does the derivative get better?
No.
And the integral grows, right? Squared x to the third, okay. So in your next process, you would have a cosine somewhere, and you'd have an x to the third. Your integral is going to explode a little bit. Does that make sense? I'll show you if you want. I think we got time for this. If you did, don't write this in. Well, I'm going to leave it up here, but you can if you want, I guess. If you did this, oops. That would be it, wouldn't it? U integral the rest of these. So that would be du equals 2 cosine 2x dx. Do you know why I have a 2 out front?
Because the chain rule.
X to the third over 3. Then I'd have uv minus integral of v du. This is my du.
Yeah.
Do you see what I'm talking about? Right when you do this, you should give up. Okay? Not calculus, all right? But right when you see this, look what happened. Look, honestly, look. This is basically the same thing, but my power grew. It didn't get smaller, it grew. Is that a good thing?
No.
Then this is the wrong thing to do. So don't try to manhandle this problem and pound it into submission, because it's going to kick your butt, all right? This thing's going to get worse. If you pick this again, well, then that's going to go to a 4. And then that's silly, so we don't want to do that. So this is a bad choice. You understand why it's a bad choice?
Yeah.
Integral got worse, not better. Even though you could do the integral of this one, this derivative didn't look better. You want both, really. You want the derivative to be better, and you want to be able to do the integral. So let's try the other one. Instead of this being u, let's pick that one being u. Then v equals, cover it, integral of the rest. du equals, this is easy part, du equals 2 dx. You guys okay with the du equals 2 dx?
Yeah.
Now, listen, you should be able to do this other thing, this other integral. Can you do this integral?
Yeah.
You might have a u substitution in there. So if you would do a simple u sub, I wouldn't pick u because you already have a u. I'd pick like a w or whatever you want, anything that you want besides x, v, and u right now. So if you picked a w substitution equals 2x, dw equals 2 dx, dw over 2 equals dx. And then do your substitution. What you're going to end up with after you do this a whole lot is you're going to understand that really what this v is going to be is negative cosine 2x over 2 is what that's going to be. Do you guys see where the over 2 is coming from? The over 2 is coming from when you have your w equals 2x, dw equals 2 dx, dw, oh, look at that, over 2. That's where the over 2 is coming from. No?
Yes.
Did I blow your minds?
It's like,
Did you follow that?
yeah.
Do I need to do the whole thing for you? No.
No.
Okay.
1/2 negative cosine w. W is 2x. That's that. It's open. Okay, now the other one. So, we've done our u, we've done our v. Let's put this thing together in the formula. The formula should look, you tell me, what's the first thing I should write here?
X squared.
Good.
X squared times
Times.
Negative
B.
cosine.
negative cosine 2x over 2
Minus the
minus
integral.
the integral
Of
of
v.
negative cosine 2x over 2.
Times what?
2x dx.
And 2x dx.
I'm going to erase this. Yeah, show of hands if you're okay with that one so far. Yes? Yes? You guys in the middle?
Oh, yeah, so, yeah, gotcha.
Let's clean it up before we go any further. That's nasty, all right? Let's make this negative 1/2 x squared cosine 2x. Negative 1/2 x squared cosine 2x. Let's do a couple things here. Let's pull out this negative and make that a plus. Let's pull out this 2 and simplify it with this 2. Can you guys see that?
Yes.
2's are gone. Let's make it plus integral cosine 2x times x dx. You could even, if you want to, move the x out front right here. X cosine x. That might look a little bit better. Let's change that. So x cosine 2x. Okay, I want to show of hands if you're okay with algebra on that one. Now, calculus is done. Just like you follow your ddx with derivatives, follow your integral for integrals. So here, can you do that integral?
Yeah, you can.
Is it in an integration table? Hmm?
No.
Is a substitution going to work?
Yeah.
Yes.
Okay, what's a derivative of 2x?
2.
So you need another part?
Having X.
You need an x, right? Would this work? Yes, if it's a square. Is a substitution going to work here?
No.
No.
Another
Oh
part.
my god. Okay, so we did, is it in the table? Will a substitution work? What's your next choice?
Parts.
You can do it again.
Are you kidding?
Now, don't screw this up. Pick the same thing for you that you did here. The same thing. It should be reduced by a power. Do you see that? This is basically the same, except instead of x squared, you get an x. That's how you know you did it right. Okay, this should at least go down a power. If it goes up a power, you pick the wrong choice. If it goes down a power, you pick the right choice. You just got to do it again. So, let's do it again. Lots of practice. So we're going to hang on to this, okay? We're going to look just right here. What's the? We got to move quickly. What's the appropriate u? Check this out. When that's x, see how when we take a derivative,
DX.
the power drops, doesn't it? 2 to 1, 1 to 0. That means that our next integral would be very easy. Our next integral would be possible at least. So v would equal the integral, cover it, integral of whatever's left, cosine 2x dx. I'm going to do this integral quickly. I'm not going to show you the substitution like here. Do you see that you're going to have another substitution here? U or W or whatever is going to be 2x. That means dw is going to be 1/2 dx. That means we're going to get an over 2. So this would be sine of 2x over 2. Can you verify that for me? Sine 2x, but then over 2 by the substitution rule. Okay, so I would not write this again right now. I'm just going to hang on to it. I'm just going to focus right here. So I'm going to have a plus, big old stuff, plus, well, we're going to have u times v u times v minus the integral of v du. Now, what's our du in this case? That's nice. That means that we're not going to have any extra work to do. I want you to see if you're okay with this one. I know I'm going about a minute or two over, but this is kind of important for us. You okay with the u? Du is dx now. You okay with the v? V's the integral of the rest. Pretty easy integral. You need to be able to take these integrals, otherwise you made the wrong choice. Now we got u times v minus the integral of v, and then du. Du is dx. Make that substitution again. Tell me something we're going to do with this. Okay, so if we do that, we get some stuff plus 1/2 x sine 2x minus the integral. Oh yeah. Yeah, that's okay. 1/2 integral sine 2x dx. Only we've already basically done that one. Look at this. This integral is that integral. So just look back at your table. You've already done it. So we have all the same stuff minus 1/2. This again was negative cosine 2x over 2. Exactly what we have here. This integral is the same as this one. So negative cosine 2x over 2. Show of hands, feel okay with that one. Now we're just going to clean it up. Okay, just clean this thing up. We've got all that nasty stuff was negative 1/2 x squared cosine 2x plus 1/2 x sine 2x. What happens here?
2 cancel out.
Oh, they're not-
Four.
And it becomes
2's do not
positive.
cancel out here.
Oh, sorry. Oh.
Plus 1/4 cosine 2x. And last little bit. Okay, I want to make sure you're clear before I let you go. This is the first little part. It's right there. You guys okay on that one?
Yep.
From the first integration by parts. This was the first part of our second integration by parts, the u times v. This little piece, this plus, comes from when we do our last integral. Minus and negative becomes a plus 1/4 cosine 2x plus c. Oh my gosh, look what happens to the powers. Square to the first power, no x at all. That happens a lot when you have this. If you add x to the third power, you'd have to do that one more time. If you add to the fourth power, you have to do it one more time. Ultimately, we're going to find a reduction formula for that. We're going to create our own formula for this. What I want to know is if that actually made, I know this is kind of sloppy, I didn't have room over here, but you understand that this is the plus 1/4?
Yeah.
Show of hands if this made sense to you. Good. All right, so for our day today, we're going to practice more integration by parts. So if you don't remember from last time, no, we've got a weekend in between this. Except for people watching online, they have like 5 seconds in between this. So for us though, what we're talking about is integration by parts. And the way we do integrals is first thing we check for is, do we have something that's in the integration table? If we do, it's really easy. It's in the table. If it's not, then we try a substitution. Once we try a substitution, well, hopefully we can do one. If we can't, we can do it because it's easier. If we can't, then we have now integration by parts. So we check this. Is this in an integration table for us?
No.
Of course not. Will a substitution work?
No.
No, if I substitute this part, there's no other e to the x in there. If I substitute this, well, there's no, it's not going to take care of the e to the x. If I do sine, there's no cosine up there. Remember, with substitutions, the derivative of your u has to be somewhere in your integral. That doesn't happen here. So what we're left with is an integration by parts. Now, these last 4 examples that we're going to do today, they're like the more difficult concepts, the more difficult ideas, the ones that are like, wow, I didn't know you could actually do that with this stuff. I'm going to show you some really cool, interesting things that you can do with integration by parts. Are you ready for it?
Yeah.
So, here's what I'm going to do. I'm going to pick u to be sine 2x. Now, as soon as you pick u, what's v? So I'll pick u. We've got to be able to be pretty good about finding out what v is. What's v? Very good. Everything else. So you just cover this up with your hand, write exactly what's left over. In this case, integral of e to the x dx. Quick head nod if you're okay with that one. So this is coming back to you, I hope, right? Now, the way that we pick u is typically u becomes easier, and you can do the integral of the v. Well, in our case, this integral is going to be really easy, isn't it?
Yeah.
This one doesn't get any better, but you're going to see something really unique that happens on these types of problems where we get, when you think about it, we're going to get repetitiveness here, aren't we? The integral of e to the x is e to the x. The integral, or the derivative of sine x is cosine x, and the derivative of that one is sine x. We're going to get things back again no matter what we choose. Does that make sense to you? So watch what can happen here. If we do this, then du equals 2 cosine 2x dx. Can you please explain to me where this 2 comes from? Hey! And v equals?
E to the x.
Do I need a plus c right now?
No.
No, we're going to wait to the very end to put a plus c. Quick head nod if you're okay with that one. Now, what we do with our integration by parts is we pick our u, do a derivative. We pick our v, we do the integral of whatever's left over. That's, the v is the rest. Then we do integral of v to u equals u times v. So in our case, our integral is going to equal u times v minus the integral of v Now, this is what's interesting. Minus the integral of v, but then we got to have du. How much is our du in this case?
2 cosine 2x.
So we need this whole thing right here. Okay, so let's make sure you guys got it. U times v, minus, okay, integral of v, du is this whole piece. Quick head now if you're okay with that one.
Yeah.
Now check it. We did this last time. We saw something similar to this last time. I'm going to move my e to the x to the front, by the way. So e to the x sine 2x. The last example that we did, by the way, what else can I do here?
And the 2 out.
2 out.
Yeah, we're going to take that 2 out because it is a constant being multiplied. E to the x cosine 2x dx. If you think back, if you watch back on the video for the last example that we did, do you remember the last one we did? We had something kind of similar to this one. We worked it down, except instead of sine 2x and e to the x, it was like an x squared. Remember that? And we had to do integration by parts twice. Do you recall that example?
Yeah.
Well, look at this one. Doesn't that look almost exactly the same as that, except instead of sine, we're going to have cosine. Could we do integration by parts again?
Yeah.
Let's do it again. Now, if you're thinking, wait a minute, wait. If I do integration by parts here, and it gets this plus something that looks almost exactly the same as that, why are we doing that? And aren't I going to get something like this with something that looks just like this again?
Yeah.
Yeah, but that's the whole point, and I want to show you why. So, we're going to leave this thing alone, and we're going to look right here. Here's the whole thing. If you pick u equals sine of 2x, what are you going to pick for u here? Pick the same thing. So, now, u equals cosine 2x. I'm sorry, not the exact same thing, but pick the same part that you picked. So if you picked sine of 2x for this one, pick cosine of 2x for this one. V, again, is the integral of e to the x dx. That's pretty easy. So u, cosine 2x, no problem. V is just the integral of the rest. Du, help me out with the du. What's the du going to be?
Negative 2 sine.
Why negative?
Because the derivative of cosine is negative.
Good, negative sign. So this is going to give us a negative sign. The chain rule is going to give us a 2. So we're going to have negative 2 sine 2x. And v is going to equal, that's pretty easy. The integral of e to the x is e to the x. Show of hands if you feel okay with that one so far. Good deal. Now, we're going to wrap this thing up. So here we go. We got e to the x. We got sine 2x. We got minus 2. We got minus 2. You guys okay with that so far?
Mm-hmm.
Now, please watch carefully. When you're doing this integral, this is minus 2 times this whole thing, isn't it?
Yeah.
So if we just start writing out stuff willy-nilly, we're probably going to make some sign errors here. So what we're going to do is, hey, if this integral is going to be u times v minus integral of v du, put a bracket here. Because what's going to happen is we're going to be distributing that negative 2 throughout this problem. Does that make sense?
Yeah.
Okay, so minus 2, no problem. Now our integral, what are we going to write first?
U times
E to the x.
U times v. So yeah, you could write cosine 2x times e to the x or e to the x times cosine 2x. It doesn't matter. It's u times v. So I'm going to write e to the x cosine 2x. U times v. We just have it in backwards order. Minus the integral of, what's going in here? That's our v. And then, v du
So negative 2 sine 2x.
times negative 2 sine 2x. Oh, I forgot something. Do you see what I forgot? Oh, my dx. dx. Sorry, I forgot my dx. Let's double check to see if I'm right. We'll go like a 10-second recap to make sure that you guys got it. So, we're looking here. It doesn't fit our table. We can't do a substitution. We're going to try integration by parts. We pick something. All right, cool. We'll pick this one. U, v is the rest. Derivative of u is this guy by chain rule. Integral of v is this guy. No problem. We do u times v minus the integral of v du. And we start over again. We simplify. See if we can move anything outside of our integral. This part, calculus is done. This part minus 2 integral. Okay, we get something real similar. Well, let's pick the same type of idea here. Let's pick cosine 2x as our u. Okay, v is the integral of the rest. Remember, we're not worried about our minus 2. That's outside of our integral. v equals integral of e to the x dx, okay. Derivative of cosine 2x, we can do that, negative 2 by the chain rule, sine 2x dx, v is exactly the same as it was before. So, again we have it, we have u times v minus the integral of v and then another du. You guys okay with that one?
Mm-hmm.
Let's simplify some of this stuff, let's see what's going on. So what can I do here? Let's do that. So, I'm going to get e to the x sine 2x minus 2, big old bracket, I'm going to get e to the x cosine 2x plus 2 integral e to the x sine 2x dx. Lots of x. By the way, I like to go slow on these ones because the worst thing you can do here is mess the sign up. That would really screw this problem up. Does it make sense to you?
Yeah.
So don't mess the signs up here. So we're going to go slow. We're going to make sure this is right. What else can I do here?
Factor out the negative two.
I don't want to factor anything. I want to get rid of these brackets. How do I do that? If I do that, if I distribute that, then what we end up getting is something really long, e to the x sine 2x, let's see, minus 2 e to the x cosine 2x. Yeah, minus 4, that's very good, because we're going to distribute. Minus 4 integral e to the x sine 2x dx, no more brackets. I want to know if mathematically you can make it there in your head, you feel okay with that one. Show of hands if you do. Now, did we do anything great on this problem? What it looks like is that, do you see what happened? Do you see this? We started here, right? You started there.
Mm-hmm.
We did all this junk. In fact, we did the jump twice. And we got down here, and this is exactly like what we started with. So you go, dang, what are you going to do? We can do it again. If we do it again,
Just gonna keep getting that and longer.
that's, what was that, Einstein's definition of insanity or something like that? I don't know who it was, but it said doing the same thing over and over again, expecting a different result. If we do this again, unless your math was completely wrong, you're probably going to get the same thing again, and again, and again. Does that make sense to you? So this is a problem. So what are you going to do about it? We're going to be smart about it. Check this out. Here's what we know. We know that this integral equals this part. Do you believe that?
Yeah.
Check this out. So what we know is that the integral, don't lose me here, this is the important part. This is easy. You can do this. Everybody can do this right now. This is the interesting part. This is why we're doing this problem right now. So we've got integral e to the x sine 2x. I'm so excited, I'm almost shaking. It's going to be so much fun. Not really, but it's going to be fun. I'm not shaking now. This thing equals, we had equals the whole way down, equals this whole enormous piece of junk. Okay, you know you've been recorded, right?
Sorry.
It's okay. You should apologize to the people. They care. I care.
Maybe they'll get excited too. when
His
they
fans
figure
in
it out.
India.
You're offending my people in India.
Oh, goodness.
Okay, that's long enough. What I want to know is, do you understand this is true? We did the integral of this, it equaled this whole mess of junk. Let's make sure I didn't miss anything. Do I have all the numbers and stuff right?
Pretty sure.
Okay. Do you believe that we have an equation here?
Oh.
Do you believe that you can do anything you want to, as long as you do it to?
Yes.
Then what if we do this? We go, wait a second. This part looks great to me. This part looks not so much. But what if I were just to take that and add that?
Oh, man.
I know, right?
Oh my god.
Here's the whole cool part about this. If you get a piece of your integral back again, like the same thing, do you guys see how we get the same exact thing back again? What can we do? Shoot, just add it to both sides. That's going to get rid of that integral. So let's see. We have one of them here. I just added 4 of them. How much do I have? I have 5 of them. So we're treating this thing like the equation that it actually is. So 1 plus 4 equals 5 times the integral e to the x sine 2x dx equals, well, this is awesome. I have e to the x, I've got sine 2x minus 2 e to the x cosine 2x. What happened to this? It's gone. I added it over. Completely gone. So the whole idea here is this. Well, maybe you're not on the wrong track. Maybe you're actually on the completely right track. You just get the same exact thing back and you go, wait a minute, man, I blew this thing up. No, you did it right. So if we have all but the last integral, and the last integral is exactly what we started with, just add it to both sides like this. Shoot, hey, we have minus 4, just add 4. Add 4 times the integral of this whole thing. It's going to get rid of it. Just like if you had minus 4x, and you add 4x. Hello, it's gone. Add it to both sides. Here's 5. We only have to do one more thing. We got to get rid of this 5. How do you do it? Just divide by 5. So I'm going to do a couple things right now. First thing I'm going to do is factor out my e to the x, so that's possible. So over here, if I factor that out, I got e to the x sine 2x minus 2 cosine 2x. So just factored out my e to the x. And then if I wanted to get the 5 over there, I do what now? If I divide by 5, I divide by 5, then I end up getting 1/5. So our integral of e to the x sine 2x dx. What we wanted to find out. We know since we divided by 5, this is gone. We get 1/5 over here. 1/5 e to the x sine 2x minus 2 cosine 2x. One thing I'm missing. What am I missing? Do the plus c. Oh my gosh. Wasn't that cool? Isn't that kind of exciting? Yeah. It's interesting, isn't it? Well, how are we going to do it? Well, if you get the same thing back again, add it to both sides. Then all you have to do is divide. This addition gets rid of the integral that you can't do. You can't do that by itself. You got to do it this way. So if you just add to both sides, you're done. Just divide by 5 and we're good to go. Show of hands if you feel okay with that one. Isn't that kind of interesting? Yeah, it's cool, right? Any questions or comments? I got to erase this whole thing right now because these problems, besides the next one, are going to take up the entire board. So every time. The next one might even take up more than the entire board. Question?
So the only time you would do that, like add the integral to the other side, is when you get the same thing back twice, when you do parts twice?
I don't know if it's twice, but if you get it back again, and there's one integral, and it's exactly like what you started with, why wouldn't you do that? You know, if it's exactly the same, you go, wait a minute. I just got back the same thing. Either I did it completely wrong, or this is perfect, because I'm just going to add that to both sides and divide by whatever the constant is, the coefficient.
Get it back. Do that.
Because you have two looping terms, would it matter if you switch the e to the x and the cosine?
I don't
for
think
u?
so, and I haven't done it. I think I did it a long time ago. I don't think it matters. My point here was to pick the same thing, though. Pick sine x, pick cosine x. If you did e to the x, you could do the integral of sine 2x, no problem. You just have to pick that again. I think this is a better way, but I haven't done it the other way. I liked it this way because it worked out really nice. I didn't have to worry about integrals. That's why I picked it, because the integral of e to the x is very easy. Question?
If this was a homework problem, is that what our answer would look like?
That is your answer.
Okay.
Other questions? All right, can we try another one?
Yeah.
I asked you a while back, when we were doing one of these things, it was integration by parts, and I said, hey, what are you going to do if I give you a problem like, I don't remember what it was, I think it was something like x ln x or something like this. Remember that? I said, what are we going to pick? And some of you guys said, well, let's pick u equals ln x. I said, really? So, u equals x, and v would equal the integral ln x. I said, well, do you know what the integral of ln x actually is? Do you know what the integral of ln x is? No, we don't. Well, now what I'm going to do is, instead of asking you this problem or something similar, I'm going to ask you this problem. What is the integral of ln x?
Using 1 over x.
I'm asking for integrals, not derivatives!
Whenever I
Ah, Hulk angry. Just joking. I'm wearing a black shirt. Right? Okay, good. Yeah, and jeans. So, do you know what the integral of ln x is?
No.
Do you know what the derivative of ln x is?
Yes.
That's 1 over x. So here's what we're going to do. We're going to make it a little bit more interesting too. I'm going to ask you, how much is this from 1 to e? Now, of course, the 1 to e part, that's really easy. We're just going to take care of that at the very end, okay? So when we're going through integration by parts, though, I really want to figure out what's the integral of ln x. Okay, well, let's start picking, let's start going through our process. Is that part of our integration table?
No.
It's about to be. Is it right now? Will a substitution work? If we do a substitution of u equals ln x, the derivative is 1 over x. Do you see 1 over x anywhere up there?
No.
Substitution won't work. The only thing we have left is integration by parts. The only thing we can pick is what?
X.
Okay, so u equals ln x. Now, if u equals ln x, see if you guys are thinking outside the box here.
dx.
How much is v?
dx?
The integral.
It's got to have an integral.
1 dx?
Integral dx. If you don't know what integral dx means integral of 1 dx. So remember how x is 1x. Integral dx is really integral 1 dx. A lot of people don't write the 1, but it's there. So let's see. Let's just start with a v. How much is the integral of dx? Or 1 dx?
X,
It's
right?
x. Yeah, the integral of 1 is just x. You guys okay with that one? We know that du equals 1 over x dx. That's actually pretty easy. We know what the derivative of ln x is, 1 over x dx. Show of hands if you're okay with that so far. Let's start putting this thing together. By the way, you don't start evaluating this right now. You wait till the very end to evaluate from 1 to e, okay? You don't have to change bounds in this, because if you think back to integration by parts, well, what happens is you're using u times v, they're already in terms of x. You don't have to do a substitution here. So don't worry about changing bounds, don't worry about that stuff. You just evaluate at the very, very end. Does that make sense to you? Okay, so we know that we can pick u. The only thing we have to pick is ln x. The rest of it is integral dx. That's x. So v equals x. We're going to do u times v minus the integral of v du. Only du is 1 over x dx. Now that's kind of interesting. You guys okay with what we've done so far? U, v, got it. Minus the integral of v, no problem. So u times v minus integral of v, and this part is our du. Look at what happens in this integral. What's going to happen?
X is kind of
What do I have in there?
the same.
1. So I'm going to reverse these because it looks a little funny. So I'm going to have x ln x minus the integral of, hello, 1 dx, or just dx again. Can you do that integral?
Yeah.
It's actually really easy. That's x ln x minus, hello? Now, if I didn't have my 1 to e, you put a plus c. If I didn't have my 1 to e, you put a plus c. That's actually the integral of ln x. The integral of ln x is x ln x minus x. Or x times ln x minus 1, if you wanted to factor that. That is the integral. We actually just did it. It's really easy if you do integration by parts. It's kind of cool though, right? We can invent our own integration tables with some of this stuff, like with integral of ln x. Show of hands if you're okay with that one. Now, if I'm asking you to go from 1 to e, I don't have a plus c because now it's a definite integral. How you write this, you don't continue to write your integral because you actually just did your integral, correct? This would be silly to write. You've done it. How you write the evaluation is you either put a bracket like this or the line or even a bracket and we go 1 to e. And then we just plug it in. So here we have e ln e minus e minus 1 times ln of 1 minus 1. Let's see what happens here. Most of this stuff should be kind of nice. How much is ln e? This is 1. So we have e times 1 minus e minus. Okay, how about ln 1? This is 0. 0 minus 1. That's still there. You don't just get zeros everywhere when you plug in 0, or when you get 1 0. So this is 1. E times 1 is e minus e. Okay, big ol' minus. ln 1 is 0. So 1 times 0 is 0 minus 1. How much is this whole thing? 1. It's 1. Now that's interesting. I think that's really interesting. Do you remember what integrals actually mean?
A reverse derivative.
It is an antiderivative. Well, what I mean is a derivative is a rate of change, or the slope of a curve at a point. Do you remember that? That's what a derivative is. What's an integral?
Area under the curve.
That's right. So a definite integral is the area under a curve between 2 points. The area under the curve ln x between 1 and e. If you know what ln x looks like, it looks like this. It crosses at the point 1. Here would be the point e. The area under this curve is exactly 1. Is that not weird? So the area under ln x between 1 and an irrational number e, 2.7, blah, 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 forever, if you find the area under there, it is exactly 1. I think that's just amazing. I don't know why, but I think that's so cool. Anyway, we can find the integral of ln x now, and we can even evaluate it with different integrals. Show of hands, be okay with that one. Interesting stuff today?
That's interesting.
It is, right? I think so. Now, are you ready for the hardest one that we're going to do today? This is going to be ridiculous, all right? We're going to have a lot of work to do. It looks so simple to start with, but it's not going to be. Okay. Here we go. Okay, I'm going to add one thing to this problem that's going to make it from easy to hard, okay? So, if I had the integral of secant x, that's actually in your integration table. Do you understand that? So you look there first. So you wouldn't do anything with this problem except go, okay, this is ln absolute value of secant x plus tangent x plus, I think that's it, plus c. You might want to look that up. That's in your table. If I did this, that's even easier. That's tangent. You're done. If I did this,
Oh, man.
we get a problem. Because that's not in my table. I can't do a substitution. Because if I pick u equals secant x, the derivative is secant tangent. That doesn't appear again. So I can't do that. So we're going to have to find out some other way to do these sort of problems. Secant to the 5th or secant to the 3rd power. I'm going to show you some techniques that we're going to get to a little bit later in section 7.2. This is kind of like an introduction to some things that we are going to be doing. I'll give you some better ideas later, but right now I kind of want to invent something with you. So here's the idea. One idea is if you don't know the integral right off the bat and you can't use a substitution, and integration by parts is kind of defeating you here because there's really nothing to work with. You get back exactly what you have here or make it worse. It's not a good thing. Well, break it up somehow into a part where at least you know how to take the integral of some of it. Like that. Why I'm doing that is, well, I don't know how to take the integral of secant cubed, but I do know how to take the integral of secant squared. Does that make sense? Mm-hmm. What you can't do, you can't break this up as secant times secant squared times secant squared. Just go, hey, the integral of secant is this times the integral of secant squared is 10. You can't do that, okay? Because that's like a product rule. That's like the whole idea of product means integration by parts, so we can't do that. So only one product. Only one product. Okay, well, let's start doing this. If I do this, I'd probably pick, let's see. Let's see what you would pick.
Secant 3x u.
Secant cubed, because I don't know how to take the integral of that part. I can take the integral of secant squared. So u equals secant cubed x. Let's do the derivative right now. If I do the derivative, I'm going to do the derivatives quick right now because I'm expecting that you guys can do this all the time, okay? The derivative of secant cubed would be 3 secant squared x times secant x tangent x. Do you follow that by the chain rule? 3 comes down, becomes a 2, leave the inside alone. Derivative inside is secant x tangent x. You guys okay with that one? Okay. If not, go back and refresh your memory on how to do integral of secant cubed on your own. V would be the integral of secant squared x dx. This is nice. I broke it up into something I can actually take the integral of. Everybody, what's the integral of secant squared? Okay. we're starting. So our first part here is we know this integral is u times v minus the integral of v du. I've got my dx again. V du. Let's clean this up just a little bit. Instead of secant squared, what am I going to put? We're going to have lots of writing going on, so I want to make sure you guys are okay on every single step. Are you okay getting secant cubed x times tangent x, u times v? Yes, no? Minus integral of v tan x. This is du. It's 3 secant cubed tan x, and then our dx. Show of hands, feel okay with that one? Okay, let's clean it up just a little bit. What are we going to do here?
3 out.
Okay, 3 out. What else?
Tangent
Square tangent.
So minus 3 integral of tan squared x secant cubed x dx. Okay, this is fun now. Well, this is fun. What do we do here? When you have something like a tangent and a secant, what you're going to see in the next section that we do is oftentimes we're going to be using identity to change one into the other. For instance, I don't want tangent x and secant x, because even if I did an integration by parts of that, it's going to be really hard to do. So let's make it easier, or maybe even impossible to do. Let's make it easier. Instead of having tan squared x, we're going to use an identity for that. What you need to know is, you need to know your identities, have them written down. Tan squared x is the same thing as secant squared x minus 1. Did you know that? This is true. So tan squared x is secant squared x minus 1. Let's use it, because now we can change our tan squared into a secant. So instead of our tan x, tan squared x, we have secant squared x minus 1, and then a secant cubed x dx. So true, that's an identity. Use it. Oh, well, wait a second. This is kind of neat. You're going to see something we just dealt with, actually. What should I do here?
Can you distribute it?
Yeah, I'm going to distribute that. Because right now, substitution isn't going to work. Because if I try this one, I don't get exactly this thing back again. Does that make sense? I'd have a secant tangent again. That would be a big problem. I don't want to do that. So let's distribute. And this is the same process that I'm going to teach you in the next section. You're going to do this a lot. So let's distribute this guy. Well, that becomes secant cubed x tan x minus 3 integral of, tell me what I get from my integral. Secant to the 5th power of x minus secant cubed x dx. Okay, really do need a show of hands if you are okay with that so far. Are we all? Cool. What can you do every time you have integral of a subtraction? What can you do? Separate it. Let's separate it. Now, watch what we're going to do. Make sure that when you separate this, this minus 3 goes to this whole entire integral. Does that make sense?
Yeah.
So when we do this, this really should have a bracket here. What we'll get is secant cubed x tan x minus 3 integral secant to the 5th power x. Hopefully you're with me on this one. Let me have your eyes on the board here. This would separate into 2 integrals, correct? It would be minus integral secant cubed. This will make it plus 3 integral secant cubed x dx. I want to make sure you're okay with algebra. It's just algebra right now, but are you okay with it?
Yeah.
Everybody, show of hands if you are. You're okay with it. Now, there's something good about what we just did. Do you see it?
Can you subtract?
What, say something good about it. What do we have good?
Can you
Give it a compliment. What do we have good about this thing?
We got the same
Well,
thing.
can you
back again.
subtract one of the integrals from the other?
This one,
Last minus.
this is great. That's great right now. Why is that great? That's this. That's fantastic, and we're going to use that in a minute. Tell me something really bad about this.
That one on the other side.
That still has an integral. So no matter what, we're going to have to deal with this one. Does that make sense? So what I'm going to do, this is why this problem is nasty. Okay. Right now, this would be awesome if there was no integral. If this wasn't here, you would just add that to both sides. You divide by 4, and then you're done. Does that make sense? This, I'm going to give us a little asterisk. We're going to have to do this one off to the side. Now, integral secant cubed x dx. Do you understand that that's really similar to this idea? Can I strip off a secant squared? If I can do that, then I'm going to do the same exact thing I just did. So I'm going to do this kind of quickly here, but you need to understand it's the exact same idea, only in this case I'm not going to have secant cubed, I'll just have secant. That means we won't have to do this process again. We'll get down to here and be able to add our integral. So we're going to do this idea twice. You're going to need a lot of practice right now. So this becomes integral of secant x times secant squared x dx. Same exact idea. Strip off something that you know the integral for. Well, then u equals secant x. The derivative is secant x tangent x dx. V would be the integral of the rest, secant squared x dx, and our v is tan x again. You guys okay with that one? Do you see the same technique at work that we just did? Strip off the secant squared. Call that your v, integral of your v. No problem, that's easy. This one, call that your u, derivative of u, you can all do that. That's secant x tangent x. Now, if we do our integral, that's going to be u times v minus the integral of v du. We'll clean it up a little bit. So, u times v, got it. Minus integral of v, hey, no problem. Du, okay, it looks kind of nasty, but we can deal with it. Got that same thing, we'll simplify it a little bit. Tan squared. Now, this looks a whole lot like that one. Very, very similar. Only instead of secant to the third, I have secant to the first. I'm going to use the same identity again. So instead of tan squared, I'm going to write that as secant squared minus 1. You guys still with me?
Yeah.
Are you sure? I don't want to blow you out of the water here. A lot of algebra, a lot of trig here. A lot of algebra, a lot of trig. So secant x tan x minus the integral of, yeah, let's call that secant squared x minus 1 times secant x. Do the same idea again. Distribute it again. That would be secant cubed x minus secant x dx. Do the same thing here that we just did here. Let's split off our integrals again. Well, if we do that, then we got secant x minus, sorry, not minus, secant x tan x minus, tell me what I'm going to have here. What's the next thing? Secant cubed x dx. Okay. Tell me what the next sign is going to be. Is it going to be plus or minus?
Minus.
You guys will see why it's going to be plus?
Oh, to the minus.
Remember, we're separating this. This will be integral minus integral, but it's in brackets. So this minus would distribute. It would become plus integral secant x dx. Oh, goodness. Almost there. Let's see. We got secant x tan x. We got minus integral of nasty thing we can't get rid of. Now this one, we can actually do that. Look back in your notes if you have to. I think I gave it away earlier, but the integral of secant x. Do you know what the integral of secant x is?
Lateral log of secant x plus tangent of x dx.
Yes, you're almost right. There's one little part you forgot.
Absolute power. So it will be natural log of the absolute power of secant of x plus tangent of x plus c.
I'm going to refrain from putting the plus c, but yeah, you're right. I'm going to refrain from the plus c until I'm completely done with my integral. I don't want that thing hanging around because it's really confusing. You guys okay with that one?
Yeah.
You sure? Have I blown your minds yet?
Yeah.
Like, what the heck? This is crazy, right? We're about 75% of the way done. We're almost done, almost. Here's what we got. We did basically a problem within a problem that was just almost as hard. Same exact idea though. Break off the secant squared. Make that your v, because you can do the integral of that. No problem, it's tan x. You got u times v minus integral of, well, v du, clean it up. Tan squared, no. Secant squared minus 1. Distribute, split it up again. This stays the same. Why do I want that to stay the same? Because it's this. It's this right here. Okay, so I gotta get rid of this in just a second. This one, I wanted that because I know the integral. That's in my integration table now. That's why we did that in the last chapter. You guys okay with this so far?
Mm-hmm.
Yes, no, yes, yes. All right. Now keep in mind, it was this that's equal to this. Tell me what I'm going to do next. Notice no integral, integral. What am I going to do?
You add the integral to the other side.
So if I add that, treat this like an equation. Add this integral to both sides. If we add that, let's see, what do you want me to erase? It's going to have to be something.
The left. I can't see the right. Thank you.
You know what? I think I can write it over here too. How much is this going to be?
Well, 2 integral secant cubed x dx.
How much that's going to equal is this thing? Is this still here? This. Is this still here?
No.
Got rid of it. Is this still here?
Yeah.
Yeah, we're almost done. Just stick with it right now. What do we do now? Why do we need to divide by 2? Is that 2 what I want?
No.
I want this without the 2. So yeah, divide by 2. So we're going to get secant cubed x dx equals 1/2 You can do a bracket around the whole thing. You can do 1/2. I'm going to do 1/2 for each of them. Secant x tan x plus 1/2 ln absolute value secant x plus tan x and absolute value. I went crazy with my absolute values. I know maybe your brains are hurting a little bit. What I want to know is, are you okay on just this piece right now? Show of hands if you are okay. Do you see how it's very similar to the first example we did today? Yeah. Really similar. You get down to one part you can't get rid of, hey, it matches up, add it to both sides, no problem. In this case, 1 plus 1 gives you 2. Just divide by 2. This piece is gone, that's great, that's what we want. We have this plus this, divide by 2, you get 1/2. You guys all right with that one? Now here's the awesome part. We're good to go on this, right? This is awesome. This piece, we're going to be good to go, as you pointed out. We're going to be adding this to both sides of our equation. You got me? This piece, we now have something for that. So what I'm going to do is I'm going to erase this part. What we know is this. This is back to our asterisk. So are you guys have any questions on this? Got to erase because I need the space. Okay, so the integral of secant to the 5th power of x dx is equal to, here's what we know. We know it's secant cubed x tan x minus 3 times the integral of secant to the 5th, again, dx, plus 3 times, here's the cool thing. Here's what we know. We wanted plus 3 times this piece. This piece is this whole mess of junk over here. You with me? So instead of 3 times integral of secant cubed x, we're going to have 3 times this whole thing right here. So we're going to have 3 times 1/2 secant x tangent x plus 1/2 ln absolute value secant x plus tangent x and absolute value in bracket. Talk about probably the longest problem you've ever done, huh?
Yeah.
Crazy. We're almost done. Almost. We've gotten rid of the integral, right? We've gotten rid of the integral. We're going to have to probably distribute the 3 to get 3/2 instead of 1/2, but that's easy. That's not a problem at all. What are we going to do next?
We're gonna add that 3 to the side.
This is the only integral that we don't like. It's already matched up with that one. Just add it to both sides. If we add 3 integral secant to the 5th power x dx, it's an equation. Just add it over here. Then I end up getting, how much is here?
4 secant 5.
Over here I've got secant cubed x. That's right. This is gone, I added it. Plus, I'm going to distribute this. 3/2 secant x tangent x plus 3/2 ln absolute value secant x plus tangent x. What's the last thing I'm going to do? Divide everything by 4. So this gets divided by 4. This is going to be a 1/4. This will be a 3/8. Does that make sense if you divide by 4? So this gets divided by 4, divided by 4, divided by 4, divided by 4. So we get the integral of secant to the 5th power of x equals 1/4 secant cubed x tangent x plus 3/8. Anytime you divide a fraction like this, just multiply the denominators and you're good. Whew, plus C. Gotta have the plus C. Oh my goodness. Do you get the idea here? Did I just lose you? I won't lose you. It's a lot. My goodness. This is like a whole page. On my piece of paper, it's an entire page. One entire page. She has a lot of things going on here. I want to show of hands if you could follow it. Makes sense to you. Good. So the idea is this. Start with something that you can actually take an integral. Hang on. Start with something you actually take an integral of. If you can't find it, split it up. Do the integral of a piece. Then see what you get. If it's trigonometric or something with an exponential or both, oftentimes you're going to get back a piece that looks exactly like what you started with. If you don't have any other integrals, you're good, like we did over here. No other integrals, no problem, just add to both sides. If you do, you might have to do the whole thing again. Take care of that integral, then you can ultimately add it to both sides, divide by your coefficient, and you're done. Okay, so the last little bit that we're going to talk about in section 7.1, I'm going to invent for you the reduction formula. What this does is when you have like a sign to some power inside of your integral and we can't take care of it just by the integration table, we can actually reduce it to a lower power of sign. I'm going to show you how to do that right now. So this is called the reduction formula. And it starts with this idea. Suppose you have some integral with sign to some power greater than or equal to 2. Now naturally, you probably wouldn't use this if you had sine to the first power. Because what's the integral of sine to the first power? Negative cosine. That's right, it's negative cosine. That'd be easy, okay? So hopefully you understand that this is going to happen for n is greater than or equal to 2. So when we don't just have sine, that would be silly to use this. But let's suppose that we do have something, some power greater than or equal to 2. So if you had sine squared x, well, we'd probably want to figure out how to do that, right? How to find that out. And one way that we're going to do these is with the reduction formula. So basically what we're going to do is do this problem in general and see what it gives us. So here's an idea. The idea is we want to split this thing up so that we can use integration by parts. A substitution is not going to work because we're going to have sines and sines. Does that make sense to you? Are you with me? Is if you okay, well, I'll show you. Here's one thing we're going to do. Right now, we can't do anything with the problem. There's no substitution that's going to work because if I substitute for sine, I get a cosine. Does that make sense? Do you see a cosine up there? Then a substitution won't work. So let's break off something. Now check this out. If I have sine to the nth power, well, let's split off 1 power of sine. If I do that, then I get sine to the n minus 1 power times sine to the first power. I need you to verify for me that this is equivalent to this. You guys with me on that one? Remember when you multiply common bases, you add exponents. So n minus 1 plus 1 gives us our n. Does that make sense? Here's what I mean about a substitution not working right now. If you couldn't visualize this in your head, visualize it now. If I try to do a substitution for sine, what's the derivative of sine? It's not sine. So this is a problem. So what we're going to do now is, well, let's go through the whole process. Does this fit our integration table exactly? Not even close. Will a substitution work? We just talked about that. No, because derivative of this is cosine, not sine. That doesn't work. So we're going to have to use parts. We have to. Now, remember when you're doing integration by parts, and some of you haven't had very much practice, I know it's a brand new section, and you haven't ever done it before. When you're doing integration by parts, you might have to do it a few times. It's not a one and done all the time, okay? Especially if you have something like, which we saw in the math lab, t cubed e to the t. You're doing that. You're having 4 integrals there. You're going to do it 3 times, integration by parts 3 times. So it's oftentimes you have to do it more than once. Well, here, and the way you pick it so that one of 2 things happens. One thing has to happen. You have to be able to do the integral of v. Does that make sense? You have to be able to integrate that. And what you also are looking for as secondary is that the derivative of the u becomes easier. It doesn't grow, it gets smaller, power-wise. Okay, those are the 2 big things you're looking for. So here, let's look at it. Now here, nothing's going to get better, okay? Nothing's going to get easier as far as the derivative goes because sine, just like cosine or any other trig function, it recycles. So we're not looking to make the derivative any easier. What we'll be looking for is something we can take the integral of. Can you take the integral of this?
No.
No, because it still has a power to it. Can you take the integral of this? Then u's going to be this thing, v's going to be this thing. Does that make sense?
Yep.
Okay, so u equals sine to the n minus 1 of x, and v equals the integral. Remember how we do integration by parts?
Yeah.
We cover this thing up. V is the entire rest of the thing. It includes an integral, it includes whatever else you have. It's horrible looking. Including the dx. Some of y'all are getting kind of sloppy on some of your integrals. You're not putting the dx, you're missing stuff. You're not putting the dx over here or the du. Make sure you have those little pieces. That's kind of important, okay? So, next thing we do, why don't you tell me, what's the next thing that we do?
You do the derivative and then integral.
Derivative, okay, so du equals, look at how this derivative is going to work. The power is n minus 1. You with me?
Yeah.
This involves what? It's going to be a chain rule. That's a chain rule. It's power rule. Power rule is a chain rule. So power rule says, watch carefully. Remember, we're just proving this, so you're not going to have to ever do this proof. I'm going to create a formula for you to use, which is kind of nice. But I want you to follow it at least. So the chain rule or power rule says you bring this down. You leave the inside alone. You subtract 1 from this. and then you multiply by the derivative of the inside, which is cosine x dx. It's just the chain rule. It says you bring down the power, got it. You subtract 1 from the power, got it. Multiply by derivative of the inside, we're good to go. Show of hands if you feel okay with that derivative. Awesome. Now, integral of, well, what's the integral of sine x? What is that? How much?
Negative cosine x.
Negative cosine x, okay. Let's see what this does for us. So we've just performed the, what was that called again? The whole process, what is this?
Integration by parts.
Integration by parts. Okay, so we're just doing integration by parts. Let's write out what it is. We know integration by parts says once you picked your u and you found your v, the integral equals u v minus integral of v du. Or in our case, u times v minus the integral of v du, where this whole thing is my du. I'm going to clean it up in just a little bit, but I want to make sure you guys are okay with this. Do you see where everything's coming from? We've got our u times our v, got that, minus, no problem, integral of, here's our v, and then this whole mess of junk is du. So we got exactly the same thing. Show of hands if you feel okay with that one. Question?
Top even dv, not just v. So we got v equals and then.
Say what now? The u goes here, we have that. Whatever v is, whatever you solve for, we don't need this, we need this. The v follows that up. So v goes here, this is this, minus, minus, integral, integral, plug this thing in again. So negative cosine x, and then du is this whole mess of junk. That's what's right, let's see where I found it, right here. Does that make sense?
Yeah.
So look at this again. Here's v, here's du, here's v, and here's u. That's what's going on.
When you find the indefinite integral of sine x, we don't have to put negative cosine x plus c?
No, the plus c is going to be one constant at the very end of this thing. This is just a temporary deal that we're doing, okay? In fact, some people show this a little bit differently. Some people show it like this. They say, well, because remember, it's u dv, right? So they show this as dv equals this. And then they go, oh, well, let's get rid of the d, let's make this v. Well, that's a derivative of v, correct? How do you undo a derivative?
Integral.
They integrate everything. We just ignore this. Integral of dv would be v, integral of this is, so we kind of skip that little part just to make it easy. It's easier to write a question.
Shouldn't the cosine at the end of du should be negative?
No, because we're taking a derivative, right? So the derivative of sine is positive cosine. The integral of sine is negative cosine. That's where we got that from. But the derivative of sine is not negative cosine, it's positive cosine. Get them straight in your head. Okay, we got to have those right. And some of you made that mistake on your last test. We've got to get these things right. You guys all clear with this one? I'm going to clean it up just a little bit. So what we're going to clean up is we're going to do, probably pull the negative out front. Negative sine to the n minus 1 x cosine x. Tell me what happens here. What happens?
It becomes a positive.
It does, because minus and negative, that's going to become a plus. Also, one of these things is a constant. What is it?
Cosine x.
Cosine x is not a constant. That is a constant. Yeah, n minus 1. That's going to be a number, right? It actually comes right from here. So we're going to have plus n minus 1 integral. Also, let's clean this up a little bit. I've got a cosine x. I've got a cosine x. That becomes... Let's see what we've done. Negative comes out, that should be easy. This becomes a plus, no problem. This is a constant, pull out in front of your integral. Cosine x is cosine squared x, and then sine to the n minus 2 power of x. Not sure if you're okay with that one. Are you still okay? Okay, it's just a little bit of algebra that we've done. Now, here's the deal. Oh, man. this right here is a problem. Because if we do a substitution with either of them, it's not going to get rid of the entire thing. We don't even know what that power is. You with me? So what we're going to do is we're going to trick the problem a little bit. We're going to call this something different. We're going to call this, using one of our identities, remember that identity? It's Pythagorean identity for sine and cosine. So here we go. We know that this thing equals negative sine n minus 1 of x times cosine x plus n minus 1. Then, okay, so cosine squared? No. Let's not do cosine squared. What we're going to do here is we're going to replace that with sine, so we have sines, and you're going to see why in just a little bit. Remember that you've done some of these integrals probably on your homework, where you have to make it down. Remember adding the integral to both sides? We get the integral back again. You're going to see that here in just a minute. We're going to get this integral back again. Remember what happens when we do that? When these things recycle, like sine and cosine does? When they recycle, oh man, I'm getting the same thing back. Is that a problem? No. Just add it to both sides, and you're good to go. You follow? So, we're going to do that in just a minute. So cosine squared, no, let's change it. This is going to be 1 minus sine squared times sine to the n minus 2 power of x dx. Let me know if I've missed anything. I've written a lot of stuff. Hopefully I haven't. Y'all still okay?
Yeah.
Okay, tell you what, next thing we're going to do. Next thing we're going to do is we're going to distribute this, because I don't like this right now. I'm going to distribute this. So we're going to have what's that going to become when I distribute this? Sine squared x.
2n minus
What do you do when you have exponents being multiplied? What do you do?
Sine to the n. Sine to the n.
Sine to the n.
Let's just add them. How much are you going to get? Okay. Okay. And remember, this is in here. So make sure I'm on my right track here. Okay. You still okay with that so far?
Yeah.
We're almost to the point where we can start adding to the side. You see, we have it right here, right? But this is wrapped up in this integral. So we're going to split up this integral. Just one big thing that you need to notice. This is n minus 1 times this entire integral. Does that make sense? Which means if I split this up, it goes to not only the first one, it also goes to the second one. Is that clear? So when I do that, we'll get, okay, negative sine n minus 1 of x cosine x, nothing changes, plus n minus 1 times the integral of sine n minus 2x dx, don't forget that dx. Here's what happens. So this, it's basically just like you drop the parentheses because you're distributing this to this first integral, no problem. What's the next thing I'm going to write? Minus. Not integral. N minus 1, yes. In parentheses. Then the integral, what's in the integral?
Sine 2x.
Sine of what?
I mean, n.
That's it. Oh, now this is cool. It's weird, right? We're doing this in general. We didn't start with any number. Nothing. That's kind of neat. So we worked this all the way down. We now have this. There's no integral there. Here we got an integral, but that's okay. We're creating a formula, okay? This part, what is this part?
The beginning integral when you started.
It's what we started with. Yeah, it recycles.
1, 2.
Recycles. Okay, so every time you've seen this before, I think we've seen it like 3 or 4 times now in this class because I want you to get used to it. This stuff happens, especially on your type of homework that you're going to be doing. What do we do to get rid of this piece? add it to both sides, it's an equation. This, we have proven that it equals this entire mess of garbage. So if we just add this, n minus 1 times the integral of sine to the nth power of x, if we add it to both sides, let's think about what happens. Let's do the right side first. On the right-hand side, this entire thing is gone. We have negative sine to the n minus 1 power of x, cosine x, plus n minus 1 integral sine to the n minus 2 power of x dx. This is gone. You guys all right with that one? Yes, no, yes, no? You sure? This is all the same, right? All the same, we just added this to both sides, therefore it is gonzo, simplified. Now, over here, this is the interesting one. How many integrals are here?
2, 1, 2.
This is just here. How many are here? So the number up front is 1, correct? 1. How many are here? N minus 1. Add them. What's 1 plus n minus 1? N. So then, I'll write in black so we can see the difference here. So that we know n times this integral equals this stuff. Now every time before, when we've had a number out front, remember n is just a number. It's like 2 or 3 or 4 or 5 or 6 or 7. What do we do with that? Let's just, if it was 3, we divide by 3. If it's n, just divide by n. So if we divide by n, what we end up getting is negative 1 over n sine to the n minus 1 of x cosine x plus n minus 1 over n times the integral sine n minus 2 of x dx. Of course, plus c, because we're talking about an integral, but that'll come at the very end. Let's make sure I did it right. Did you guys see where the 1 over n is coming from? Divided by n. Here we have n minus 1. Well, now we're dividing it by n. There's only 2 terms, this one and that one. This right here, this is the reduction formula for sine. Now, if you're thinking, that's a lot harder than just doing the problem, it's really not. I'm going to show you. Do you want to see an example of how this stuff works? I'm going to have to erase the board, though, so show of hands if you feel okay with the proof.
Wait, just do it.
I'm just going to erase this side. Are you guys okay with getting this far?
Yeah.
Didn't make sense on how we got that far. You just have to use it. I just want to make sense to you where it came from, that it wasn't just magic, okay? So, reduction formula. I'm only going to give you one example on how this actually works. I think one example will make it very clear on how it works. So here you go. Isn't it kind of a cool little proof, though? It's interesting, right? It's a really nice little proof. Add to both sides, like you've been practicing, divide, you're good to go. Kind of neat. And what this allows you to do is this. If you got an integral of sine to the 4th power of x dx, sine to the 4th power of x dx, you start thinking, you go, wait a minute, how in the world am I going to do that problem? I don't know. I mean, does it fit the integration table the way it is right now? Does it? Will a substitution work? Remember, if I pick sine, the derivative is cosine, it's not up there, so that would be a problem. Integration by parts, will it work? Yes. Yes, it will. But we've proven that we can actually do this every single time we have any power greater than 1 or greater than or equal to 2. Well, check it out. Here's how it works. What's your n? 4. So this is sine to the 4th, so our n would be 4. Here's how you work it. It's really nice. What this integral is going to equal, let's read it. It's going to be negative 1 over what? 4. Negative 1 over 4. What's the next thing I write? Sine of where are you getting the 3 from?
4 minus 1.
Right there, 4 minus 1. X cosine x. So let's see. N was 4. So negative 1 over 4, got it. Sine to the 4 minus 1 is 3. X cosine x, then we're going to put a plus. Again, yeah, n is 4, so n minus 1, that's 3 over 4. What's the next thing we have? It's an integral. You're still going to have an integral. That's why it's called the reduction formula, because it's going to reduce the power of the sine by 2 every time. Do you see that? By 2. So instead of having sine to the 4th, now we're going to have an integral. It says of sine. Good. Yeah, n is 4. 4 minus 2 is 2. And it just made it a little bit better. Isn't that kind of nice? Is it easy for you? It's just a formula, so it's kind of nice. That way you don't have to waste a lot of time on integration by parts. Make sure I got that right. Questions?
So then once we get the integral of that, we can still keep going by plugging in.
That's the question. Does this now fit this model? Shoot, just do it again. As long as the n's greater than 2, greater than or equal to 2, if it's 1, you're good to go. So if this is a power 3, you'd be done right now, because you'd have the integral of just sine to the first, right? Integral of sine is just negative cosine. Hey, you're done. So we just do this one more time. So we rewrite everything. It's just this little piece. Remember, this is in a bracket. Some of you are in the very bad habit of not writing parentheses. Parenthetical expressions in mathematics are absolutely crucial. It allows you to distribute, allows you to see what's being multiplied, order operations-wise, what's being added, subtracted, and not being multiplied, okay? So they're very important. So when we have this thing, when we do this little segment, well, we can do the same thing. Just be real careful that you know this positive 3/4 is going to distribute across both of these terms. Does that make sense? That's huge. So for us, why don't you do it? Just do this little piece, sine squared x. Do it just like that, okay? Just write out what that little piece is. Okay, what's our n again, people?
-1/2.
What's our n?
2.
So just plug in the 2 everywhere you see the n. Yeah, 2 minus 1 is 1. That's cool. Cosine x. I have to erase this part now. Plus. Okay, 2 minus 1, that's 1 over 2. Integral of... Please be careful when you do this. How much is... What's our n? What's 2 minus 2?
0.
What's anything to the 0 power?
1.
Don't you be putting a sign there. That doesn't make any sense at all. If you put sign, then this would have had to be a 3. Does that make sense?
Yeah.
Hello, yes, no.
Yes.
Sign, some of you it doesn't make sense. I can tell in your eyes. 2 minus 2? Anything with 0? 1. Dx. You don't even really need the 1 there, but we can have it. So this would become -1/2 sine x cosine x plus 1/2. Hey, what's the integral of 1?
And
There we go. Now, just keep in mind that this whole thing, there's a 3/4 in front of it, and a plus in front of that, and a cosine x, and a sine to the 3rd power of x, and a -1/4. This has to distribute, which is not a problem. You just can't lose track of it, because that would be a problem. Quick head nod if you're okay with that so far. Do you see how much faster this makes integration by parts if it's just sine to some power? That's kind of nice. So here we go. We've got, final answer, -1/4 sine to the 3rd power of x, cosine x, minus 3/8, hopefully you see where that comes from, sine x cosine x, plus 3/8 x. And lastly, what do we always have when we're doing indefinite integrals? Yay! There we go. Cool? Kind of cool, right? Work anytime you have just a power of sine to some power greater than or equal to 2. That's the idea. Show of hands if you feel okay with that one. Awesome. Now, we're actually done with section 7.1, finally. Oh my gosh, thank goodness. It's taking us so long. It's taking us like a week. Michael?
Is there a reduction formula for the other trig functions?
For cosine? Yeah, I think you can create one for cosine. I haven't done it. I just want to see that this was possible. Why don't you, I'll bet you guys could work on it, see if it is possible.